Hi, in today's lecture, we are covering a fascinating topic which I really like. It's about equation discovery using machine learning. Specifically, we will see how we can make use of scientific machine learning to identify the way in which a particular variable is changing with respect to time or with respect to space. And that is what I mean by equation discovery. This is very powerful because if we had a way to discover how the format of an equation is, we can basically uncover the mechanisms behind various phenomena. So in traditional machine learning, we know that it requires large amount of data. There is even a field, right, called big data analytics. But what we should understand is that there is an analog of a picture is worth 1,000 words in the context of scientific machine learning, which is a model is worth 1,000 data sets. So if we have a mathematical model which describes a phenomenon, then that is more powerful than the data that we collect from actual experiments, because this model is now condensing all the things that you have from the data set into one single equation or a set of ordinary differential equations or partial differential equations. So this is very powerful. But the problem in reality is that often these models are inadequate. Sometimes there are so many assumptions behind these models that they cannot approximate real life data to a degree of accuracy that we would like, right? So that is the problem. However, you should understand that in many branches of science, even if you wanted to implement data set for building a machine learning model, it's not available because many times conducting actual physical experiments are costly. Except in few fields of science, like for example bioinformatics, there are a lot of large amounts of data available in bioinformatics. But if you are studying astronomy or maybe quantum physics, maybe getting data set would require setting up experiments that may cost you millions of dollars. So the data might be very scarce. So in such case, what can you do where you are not throwing away your mechanistic or phenomenological models, but you are keeping what you know, but you are also incorporating deep learning or machine learning technique into this. So you are not looking at big data anymore, you are looking at small data, you are looking at mechanistic models, and you are looking at a combination of these two things to produce something even more powerful. So this is what scientific machine learning is all about. So let us discuss today how a structure called as UDEs, Universal Differential Equations, can be used even in the absence of enough data to make very meaningful predictions or even to discover unknown equation structures in a particular phenomenon. So in many domains of science, mechanistic models are deployed mainly because it's very accurate, it's predictable, it's very interpretable. Whereas the advantage of ML models is that they are flexible to adapt to actual changes happening in real world data, right? So it's in your best interest as a scientist if you can incorporate ML into your mechanistic models. So today let us discuss an approach called as UDEs, Universal Differential Equations. Universal differential equations are defined either partly or fully by any type of universal approximator. A universal approximator is a function which allows you to approximate any universal function. So let's say you have data set corresponding to which is generated by simulating some function, right? This function can be of any degree of complexity. A universal function approximator is a way in which you can define a parametric function. One example is Fourier series, right? So Fourier series can be fit on a square wave. So for example, let's look at some images over here. You can construct a square wave effectively by combining these sinusoidal waves of different frequencies together. So here in this picture, if you zoom in a little bit, let me just open this. You can see that, so this is a square wave. Here, this is how a sinusoidal wave looks like when you are putting it on top of the square wave. Here, I think it's a combination of two sinusoidal waves with some offset, multiple sinusoidal waves. And if you have enough number of sinusoidal waves of different phase, which is offset, and when you superimpose them, you can approximate this square function to a certain degree of accuracy. So this is one example of a universal function approximator. I don't know how many waves are superimposed here in this example. Maybe this page will give us some idea perhaps. So here you can see that you are superimposing maybe 1, 2, 3, 4, 5, 6 waves or something like that, right? So there should be, I think, 6 parameters, the wavelengths. So you are superimposing them to get this effectively this square wave. So this is a parametric model. It's also a universal function approximator because irrespective of whether your wave is a square wave or if it is some other weird, maybe some kind of ratchet kind of wave, it does not matter. You can approximate it. You need appropriate amplitude, you need appropriate frequency, and you need enough number of waves to superimpose, and you can construct this. Another example of universal function approximator is our neural networks. Neural networks operate in higher dimension, meaning it can have more number of nodes, which will allow you to approximate much more complex functions. So if you can approximate a function with just less number of parameters, Fourier series is a good choice. But whenever the number of dimensions increase, whenever the complexity of the function increases, you may need more and more parameters to approximate that function. So as a higher order universal function approximator, neural networks are a better choice. So today we'll be looking at neural networks as universal function approximators to be used in the structure called as universal differential equations. So why do I call it as universal differential equation? There is this beautiful paper written by a team of researchers from MIT. Let me see if I can open this. This is published in Archive on universal differential equations for scientific machine learning. So Dr. Chris Rakaukas is at MIT. Professor Alan Edelman is also at MIT, the founder of Julia programming language. So this paper is very beautifully written, and this paper is about how you can approximate models. For example, models for biological systems or chemical reactions or heat transfer or climate model, even in the absence of data. And here they come up with this term called universal differential equations, which denotes the presence of an ordinary or partial differential equation, right? So ordinary differential equation could be of the form d by dt of some parameter, let's say y, equal to f of some t, let's say. Partial differential equation would be of the form dou y by dou t equal to, here maybe I can also put some other variable x comma t, f of t comma x. So this is partial differential equation. But let's say you have something of the form this plus some kind of neural network, which is also a function of certain parameters theta, certain parameter theta. This is called as a universal differential equation. So this is like a universal ordinary differential equation. This is a universal partial differential equation. In general, you can call this as a universal differential equation or UDEs. And why is it called as a UDE? Because part of this system, part of this equation is represented by a universal function approximator, which is a neural network. In lower dimensions, of course, this could be done with a Fourier series, but that is not what is done here, right? So this is the idea behind universal differential equations, where you know the phenomenon partially, you know the mathematical description of the phenomenon by f of t comma x. So this could be of the form, let's say you have a heat transfer. So dou t by dou t. So this is rate of change of temperature with respect to time is alpha dou square t by dou x square plus some kind of source term, which is unknown, right? Say source of time. Now here, this part, which is called as a diffusion part of the temperature, it is known. So here you are using a mathematical structure. This is the partial derivative of temperature. But if this source term is not known, maybe you could replace this with a neural network term. And then the combination of these two things can now try to predict your rate of change of temperature in a much better way, right? So this is an example of universal differential equation. In fact, we'll be today looking at a temperature problem only, heated one-dimensional heated rod. So we'll come back to that in a moment. But basically, for all the practical purposes of this lecture, whenever I say universal function approximator, you can imagine a simple neural network, simple feed-forward neural network. Okay. So now let us come to the problem that we are looking at today so that we can understand this whole idea of implementing UDE for certain cases. And as I mentioned in the first part of today's lecture, today is about equation discovery. So we will assume that we don't know the format of the equation, and we will see how we can recover the form of that equation using scientific machine learning framework. So that is what we are going to do. So in this 1D heat equation, we are looking at a metallic rod, and this rod has a length L. You are looking at the origin at one end of the rod, and the other end could be L, where L could be 1 if you are normalizing the length. Now we assume that this rod is preheated to some sort of temperature distribution T of X. So at time T equal to 0, the rod is already heated to some temperature. Maybe this temperature distribution is uniform. Maybe this entire rod is initially at 300 degrees Celsius and then it's later cooling down. Or maybe the temperature distribution on the rod is like a wave pattern, or maybe like an amplitude where the both ends of the rod are relatively cooler, middle of the rod is a bit hotter. So there can be any type of initial temperature distribution on the rod. Then we are allowing the temperature distribution on the rod T of X to evolve over time. So effectively, the temperature is a function of both X and time. The temperature at any point in the rod will evolve over time. Similarly, at any given point of time, each point in the rod will have its own unique temperature. So the question is, how do we calculate the evolution of temperature, which is T of X comma T? We can take a few assumptions here. First assumption is there is no convective or radiative heat transfer, meaning the rod is not losing heat to the atmosphere or to outside the rod through convection or radiation. There is also something called as a periodic boundary condition or circular boundary condition. What I mean by that is, in this example, imagine you had a circular rod, right? So let's say your rod was like this. This is X equal to 0 and this is X equal to L. Then you repeat this rod over here. Then you repeat this again and again. And again, I'm sorry, this is supposed to be a circle, but I hope you get the point. So you repeat the rods such that if you repeat the rod like this, in the absence of any sort of convective or radiative heat transfer loss, what happens is whatever temperature, whatever heat flow is happening at this end of the rod, it is going into this rod, and this is the X equal to 0 and X equal to L of this rod. This is X equal to 0, X equal to L, X equal to 0, X equal to L, X equal to 0, L, 0, L, 0, L. So if you look at it, whatever is leaving at X equal to L is entering at X equal to 0. So this is called as periodic boundary condition. So whatever enters here, exits here, should come back here effectively, right? So that is what is called as, it can be called as circular boundary condition or periodic boundary condition. So this is one thing which we are using in this particular lecture. Of course, we can use other boundary conditions also. We can assume that one end of the rod is insulated. If it is insulated, there won't be any heat flow here, which means the gradient of temperature, for example, dou T by dou X at X equal to L equal to 0. So this is what it means to have an insulated end, but we are not using this boundary condition. But it can be used if you want to use. It's very easy. So this is the problem statement. Now, what does the rod heat evolution look like in theory? In theory, if we ignore all the other effects, if we ignore the generation of heat, if we ignore convection, if we ignore radiation, the only thing that happens is diffusive heat transfer within the rod. So within the rod, over the length of the rod, the temperature will keep evolving as a function of time. The hotter regions in the rod will give heat to the colder regions in the rod, and the hotter regions will cool down, colder regions will heat up. So this is what is going to happen. And at the end, eventually the rod will become almost uniformly heated. So this is what will happen to this rod if we have periodic boundary condition. And the heat equation, which is partial differential equation, it's first order in time, second order in x. It's dou T by dou T, where T is the temperature, equal to d dou square T by dou x square. So here D is sort of like a diffusion coefficient. In many contexts, I think people also use alpha. Here we are using D. So in classical partial differential equations, we know the exact physical form, right? We know what is the value of this diffusion coefficient, whether it's a constant or whether it changes with respect to the space, whether there is a heat generation term, which means there will be an additional maybe generation term here, whose form may be known. So this is how it will look like if we know what this phenomenon is represented mathematically. Here is actually a website which is very cool. It allows you to visualize partial differential equations, many partial differential equations. So this, what you see here, is like a heat equation in 1D. What you see is initially it was like a sine wave, then it's flattening. So I have closed the interactive simulation website because my video recording is slowing down a little bit. I think it's maybe because they are calculating, I mean, they are solving the PDE using JavaScript on the browser itself, perhaps. But anyways, I recommend you to just go through this website. It allows you to visualize two-dimensional heat equation where there is dou square T by dou x square and dou square T by dou y square term. And you can see how the heat distribution changes over time. Eventually what happens is, if you have a rod like this, and if the temperature distribution is like a sine wave, right? If it is like this part is hotter, this part is colder. And if this is the average temperature of this sine wave, then basically the equilibrium after infinite time will be something like this. The temperature will equilibrate such that the hotter regions will become colder and colder regions will become hotter. And this evolution over time and also space is described by this partial differential equation. But here are some issues which may happen in a real life. In real life, you probably don't know what the diffusion coefficient looks like, what its value is. You probably won't know whether the D is a constant or whether it spatially varies, meaning whether it's D of X, right? This you don't know. Sometimes you may not even know that this operator, this is Laplacian, whether it is Laplacian, or how do you know whether it's of the form dou square T by dou x square, or let's say dou cube T by dou x cube, or something else. You don't know, right? So there are cases where if you are looking at a phenomenon completely from scratch, you probably have no idea how to describe it. So this is where we are bringing something called as universal partial differential equation, or universal PDE, into picture. In general, you can also call this as universal differential equations. The differential equation itself can be partial or ordinary. So here we can convert this normal partial differential equation into UDE by converting first of all, the diffusion parameter into a learnable parameter. So this D cap means diffusion term is learnable using a neural network, of course. And here the temperature spatial variation you are trying to approximate using a convolutional neural network. Now you might obviously be wondering, you might have multiple questions. First of all, how do I know that I should use these two terms? How do I know that I should use a diffusion term and I should use a neural network like this? And why it should be a convolutional neural network? What should be its format? I'm sure you have multiple questions. So we will address all of those questions one by one. But here the basic idea is this: we will allow eventually this diffusion term, this learnable diffusion term, to approximate the actual value of diffusion coefficient, right? And we will do this using data. So first we will solve the partial differential equation to generate ground truth data. And we will see if we can teach the neural network to approximate the diffusion term. Second thing is, we will use a convolutional neural network where we have a stencil. Now, I'm I'm 99% sure you have not heard of the term stencil in this context. Maybe you have, but if you were hearing this for the first time, like how I was when I was learning this concept, don't worry. We'll discuss about this stencil in detail. Stencil, you can imagine like a kernel in convolutional neural network. You have a kernel which moves through the image, right? Here also something similar is happening. So stencil is sort of, for now, you imagine it like a kernel. I'll tell you exactly what it looks like. So don't worry about the term. It may look unfamiliar, but it's fairly simple to explain. We also want to retain the physical structure of our heat equation. Now, what is the physical structure? It has a rate of change of time kind of term. It also should have some kind of dou by dou x term. It may be dou by dou x, it may be dou square by dou x square, dou cube by dou x cube, whatever. But there should be gradient in space and gradient in time. These two things should be there in the physical structure of heat equation, and only diffusion is happening. So that we are already told, like no other heat transfer is happening, no generation, no reaction, no heat sink, no radiation, no convection. So all of these are mentioned. Only thing that is happening is conduction through the rod. So we know diffusion is the phenomenon. We just don't know the coefficient. We also don't know the format of the spatial gradient, right? So these are the problems. Now, first of all, let us talk about the two terms that we are recovering. So the two terms are first D cap. D cap is the predicted value of D. It's a parameter which scales whatever prediction we make for the equivalent of dou square T by dou x square, right? So in the heat equation, dou T by dou x, dou T by dou x, not dou x, dou T by dou T is proportional to dou square T by dou x square, right? So whatever is the dou square T by dou x square value, you are scaling it using the diffusion parameter to get the exact value of rate of change of temperature, right? This is what you're doing. So this is a scaling parameter, which we will use as a learnable layer in our entire neural network structure. I will draw the neural network structure and show you exactly where this diffusion parameter is coming. Then the second term is the convolutional neural network term. This convolutional neural network, using this convolutional neural network, we'll try to recover the exact form of the second order derivative term, which is dou square T by dou x square. Now, here I have written stencil-based recovery. So let us discuss what exactly is this stencil-based discovery. What is stencil? So let's discuss that. A stencil is like a convolution kernel. So if you Google convolution operation visualized GIF, you will see a lot of GIFs which explain the process of convolution. So here, for example, in this GIF, you can see the kernel moving. So this 3x3 matrix is the kernel. It's moving over this image. And you can see that the value of the output matrix, so this pixel value is influenced by not only the corresponding pixel over here, but also the neighboring pixels. Because here you're looking at total 9 pixels to calculate the value of 1 pixel in the output. So similarly, a stencil is primarily used in discrete mathematics. It's a set of weights which allow you to, let's say, estimate first derivative or second derivative or any derivative at a point using the neighboring points. So for example, if you have a function f of xi, where I runs from 1 to 100, so you have 100 data points like this. Now you can define various types of stencil. So that stencil could be a set of weights, right? So let's say there are 4 weights or 5 weights, let's say. So this is 1, this is 2, this is let's say -1, this is 1 by 2, and this is 3. And the values of f of xi, let's say they are 23, 42, 1, 31, whatever, some set of numbers. Now using this stencil, we could estimate maybe the value of an output one-dimensional array such that the value of this data point will be 1 times 23 plus 2 times 41 plus 1 minus 1 times 1 plus half times 31 plus 3 times 7. So you can do a weighted sum of all of these numbers using the weights of this stencil as the weighing factors, and attribute that to one single data point in the output. If you remember, if you look at the convolution operation done using that kernel, this is exactly what happens. So I will tell you how to use a stencil to get a derivative. So if you are looking at a stencil of the form, let's say -1, 1, right? So let's say this is your stencil and this is your data set. 1, 4, 7, 2, 5, something. This is your data set, which is equal to f. So f of xi is this. Now, if you want to calculate that the derivative of f of xi, what would you normally do? You simply take the difference between the neighboring element and divide by whatever is the distance that separates them. So if the distance that separates these two data points is delta x for all of these, then your derivative is nothing but 4 minus 1 by delta x for this guy, 7 minus 4 by delta x for these two pairs, 2 minus 7 by delta x, etc. So what is this 4 minus 1 by delta x? 4 into 1 plus let me write it as 1 into 4. 1 into 4 plus minus 1 into 1 divided by delta x, right? And this can be written as 1 into 7 plus minus 1 into 4 divided by delta x. So here the common thing is a stencil whose first left side value is 1, right side value is -1. Left side value is 1, right side value is -1. So irrespective of what numbers come here, a stencil of the form -1, 1 can be used to approximate the first derivative in a one-dimensional array. If it's a two-dimensional array, you will need a stencil which has more values, but I hope you get the basic idea. So this is the idea behind, this is the concept behind a stencil. So in this example, so let's say you have a function whose curvature you want to estimate. And if you have a stencil like 1, -2, 1, then what you do is, if you have an array of points, and let's say this is the ith point called row I, then this will be row I minus 1, and this will be row I plus 1. Then you will first take the row I minus 1 and multiply by this guy. You take row I, the middle guy, and multiply by -2. You take row I plus 1 and multiply by 1. Then you sum all of that. And that is the output you obtain by applying the stencil over your data set, right? So very much similar to how you calculate numerical derivatives or numerical second derivative. Same thing which I mentioned in the convolution operation. If I play this GIF, here also exact same thing is happening. -1. So if this array is -1, -2, -1. So this is like a edge detector. -1, -2, -1, 0, 0, 0, 1, 2, 1. You are multiplying -1 with 75, -2 with 80, -1 with 80, 0 multiplied by these three numbers, then 1 times 70, 2 times 75, 1 times 80. So that will be, I think, just these two guys will cancel. So it will be net minus 75, I think. So it will be minus 75 minus 160 minus 80, then that will be cancelled with this plus 80. So basically the second term, whatever is going to come here, I think it would be minus 10. I'm not sure. We can play the simulation and see what is the output. It's minus 15. Okay, maybe, yeah, I have probably done a calculation mistake, but basically I hope you get the idea. So if I want to look at this as the region which of interest, so then all of these are invalid because they are getting multiplied by 0. This is also 0. So it will be minus 75 plus 80 plus 75 into 2. So that will be 150 minus 75 plus 80. So that will be 75 plus 80, which will be equal to 155. Yeah, and here you can see that the output is 155. So this convolution operation also works pretty much similar to that of a stencil. So that is what I mean by DOT by DOT approximated using two learnable parameters. First learnable parameter is the scalar, which corresponds to the diffusion. Second is the convolutional neural network, which is literally the stencil. Now, what is the format of this whole neural network? We will come to that. Now, let us address the elephant in the room. You may have two questions. I also had. Why are we only recovering these two terms? Why are we only talking about diffusion, decap, and some stencil term? Why? Um, and what is the mathematical format of this learnable stencil? Is it having 3 terms? Is it having 5 terms, 7? What's the logic? Are there any constraints to the numbers which are part of the stencil? For example, if I have 3 numbers which are learnable in the stencil, I can write it as W1, W2, W3. And I say these 3 are weights which are part of the neural network which can be learned, right? So, but then there will be questions. Why 3? Are there constraints for these 3 numbers? So we will discuss that soon. So let us first discuss these two questions. Firstly, why are there only 2 terms? So let's look at the phenomenon that we are exploring. It's one-dimensional heat equation. We are already told that diffusion is the only thing that is happening. There is no local reaction term to produce heat or to consume heat. So this thing is not there. There is no advection. There is no forcing term. Maybe forced convection is not there. There is no radiative heat transfer loss or heat transfer gain. Pure diffusion, which means the only 2 things we can expect is a diffusion coefficient. And we know that diffusion happens in presence of some sort of gradient, whether it's the second derivative of the gradient or the gradient itself. It's yet to be seen, but there has to be a spatial gradient. This is the logic behind assuming only 2 terms which are learnable in our universal differential equation for this problem. For another problem, it will be completely different. You will not be just picking two terms, right? So I have deliberately picked a simple enough problem statement so that only 2 terms are there. So that's the main thing. Now the question is, what about the stencil format? So the format we are using in today's lecture would be a stencil with 3 weights, W1, W2, and W3. And what would the operation of the stencil look like? As I mentioned, if we are looking at TI meaning temperature at the ith spatial data point, temperature of xi, that is what is TI, that is what TI means. So TI will be multiplied by the middle weight. So stencil here will look like W1, W2, W3, and W2 will be multiplied with TI, W3 with TI plus 1, and W1 with TI minus 1. Okay, so now one more question. Why are we having only 3 terms in the stencil? Are we now assuming that we know something about the format of the spatial gradient? Because initially we discussed that we don't know much about the spatial gradient. So now what is the basis of selecting these 3 stencil with 3 weights? Let's come to that. But the way in which stencil works is the following. We have 3 learnable weights, and we are modeling the rate of change of temperature as some diffusion parameter decap. This is the scalar, and some spatial operator, right? Spatial operator need not be this Laplacian. It can be anything. So although we are not explicitly assuming dou square t by dou x square spatial operator, you will see that the stencil that we are going to choose will almost look like dou square t by dou x square, or it will have a tendency to look like that. So if it was a dou square t by dou x square operator, right? What is this? This is approximately dou by dou x of dou t by dou x, correct? Now let us try to first approximate dou t by dou x numerically. This is approximately t I plus 1. So let's say this is dou t by dou x at I. Maybe I can approximate this as ti plus 1 minus ti divided by delta x, correct? Now let us call this as the ti prime. So what is dou by dou x? This is dou by dou x of ti prime. And what would this be? This would be equal to, let's say, ti prime of xi, or ti prime minus ti minus 1 prime divided by delta x. And if I expand both of these, this would look like ti plus 1 minus ti divided by delta x minus ti minus ti minus 1 divided by delta x, the whole divided by delta x. So this will be, if I expand the numerator, it would look like ti plus 1 minus 2ti minus 1 minus 2ti plus ti minus 1 divided by delta x square. So this is how the expansion of, numerical approximation of dou square t by dou x square can look like. So what is this stencil? What does this stencil look like? If it is a stencil of 3 weights, it will look like 1, comma, minus 2, comma, 1. Because ti plus 1 is multiplied by 1, ti is multiplied by minus 2, and ti minus 1 is multiplied by 1. So it's like a stencil. This is like a stencil operation numerically with 3 weights of 1, comma, minus 2, comma, 1. So given that the numerical approximation for the actual Laplacian operator is like a 3-point stencil or 3-weight stencil, you could ask me that, okay, if that is the case, then why are we directly taking a 3-point stencil as the approximation for the for this term, for the convolutional neural network term? So there is a logic behind that. It's not random. I understand that it's very convenient because the stencil that we are taking is 3-point stencil. The stencil which we are supposed to learn, which can actually approximate a Laplacian operator, is also 3-point. It's minus 1, comma, sorry, it's 1, comma, minus 2, comma, 1. So here there is a reason why we are picking 3-point stencil. Firstly, it is like you are assuming that the spatial gradient or spatial second order derivative, any order gradient, is only dependent on the point itself and its two adjacent neighbors. So if I is the point, then the spatial operator depends on I plus 1 and I minus 1. Okay, so it's called as a locality assumption. You're looking at the immediate local neighborhood of the point. Second is a 3-point stencil is non-trivial. Non-trivial as in you have 3 weights to learn, and it won't be of the simple format 1, comma, minus 1. If it was a 2-point stencil, maybe the gradient could have been simply t of x minus t of x minus 1, t of xi minus t of xi minus 1 divided by delta x. Then it would have been 1, comma, minus 1. It is a trivial stencil operator, but learning a 3-point stencil is not straightforward. Then the third thing is, if you can approximate the data points which you get by solving your partial differential equation, so you will have a ground truth, right? At the end of the day, whatever universal differential equation framework you have, it is used for predicting a temperature. Then the temperature you predict is compared with the temperature that you actually know as the ground truth. Then the difference between those is used to construct a loss, and that loss is used to construct a back propagation, which will allow you to modify the weights of your neural network. So if a second derivative like operator can sort of approximate your actual training data very well, why not? So we can explore like this. But in general, if you are working with a truly unknown problem where you have no idea what kind of stencil to take, you can start with a stencil of maybe 2 weights and then go up. Start with a stencil of 2 weights, see if you are able to approximate the data, then go to 3 stencil, 3 weight stencil, then go to 4 weight stencil, etc. In this case, we are skipping the 2 weight stencil. We are directly going to the 3-point stencil. Okay. So here I have just written the derivation of the dou square t by dou x square Laplacian operator and how it relates to the 1, comma, minus 2, comma, 1 stencil. This is like a CNN kernel, but I already showed you this derivation. Now there is one more idea here. There is a constraint that we have to apply to this stencil. I will come to that. But the way in which stencil is applied, I hope you understand. It's W1 times Ti plus 1, W2 times Ti plus W3 times Ti minus 1 by delta x square. Not delta of x square, delta x the whole square. Okay, like this. Now there is one more constraint that we have to apply logically to this stencil, and this will also allow us to perform the training much better, which is sigma of the weights of these stencils should be 0. So we'll also enforce this constraint. You might be wondering why. Why is this being done? So this comes from a more like a physical knowledge perspective of the system, and this is where you see the true power of scientific knowledge is coming into the machine learning. So let's say instead of temperature, you were looking at the quantity density of matter in space and time. Okay, so rho of x comma t. Then you know that the mass that is there in a certain space, certain amount of space, is simply sigma I of rho I, right? That is mass. And we know that mass is neither created nor destroyed normally. So we want mass conservation to be applied here. So d by dt of this m, if provided that space is constrained, is zero. So you should not have the total mass changing in the system. So now let us apply this d by dt of m equal to 0. So d by dt of rho should be, and this is d by dt of density, not temperature. So here we are, for a moment, we are ignoring the temperature. We are looking at density and mass. So d by dt of rho should be some kind of mass diffusion term multiplied by stencil. So this is exactly what we were formulating, right? For the temperature problem. Here we are doing it for the density problem. And stencil is nothing but W1 rho I plus 1 plus W2 rho I plus W3 rho I minus 1. This part is fairly straightforward from our previous discussions. So if the mass is sigma times rho, we know that so m equal to sigma I rho I. Then we were saying that dm by dt is equal to 0. But what is dm by dt? It is d by dt of sigma rho I. So here what I can do is I can bring the d by dt inside the sigma. So this will become sigma d by dt of rho I, correct? And we wrote that rho I is approximated as a diffusion term multiplied by, no, not rho I, d by dt of rho I was approximated as diffusion terms multiplied by stencil of ti, right? So what was this? This is equal to sigma d multiplied by stencil of ti. So this we had mentioned here. D by dt of rho I is d multiplied by stencil of rho I. Okay, sorry, not Ti. We are not looking at temperature anymore. We are looking at density. So rho I. And this can be written as d multiplied by sigma stencil of rho I. So it iterates over I. So what is this stencil rho I? This is equal to d multiplied by sigma I. We had discussed what is stencil of rho I. That is W1 times rho I plus 1 plus W2 times rho I plus W3 times rho I minus 1. So this was stencil of rho I. So it's a sigma over this. Now we can again expand this. This is equal to d multiplied by sigma I W1 rho I plus 1. This is the first term. Then the second term would be plus W2 rho I, sigma of this plus is also over I. This is also over I, W3 rho I minus 1. Here W1, W2, W3, they do not depend on the index I, so they need not stay inside the summation. So this can be also written as W1 sigma I rho I plus 1 plus W2 sigma I rho I plus W3 sigma rho I minus 1. Okay, so here actually if you look, it's the summation of rho. It's just that the index is I plus 1 instead of I. Here index is I. Here index is I minus 1 instead of I. But at the end of the day, you are performing a summation of rho for the entire possible values of its index. So the summation of this is the mass m. Summation of this is also the mass m. Summation of this is also the mass m. So this can be written as, this is equal to d multiplied by W1m plus W2m plus W3m. So we can bring m outside. So this is equal to d multiplied by m multiplied by W1 plus W2 plus W3. But what are we doing? We are doing d by dt of mass here. We are still doing dm by dt because m equal to sigma rho I, and we were doing d by dt of that. And we said that because of mass conservation, d by dt of m is equal to 0. So this guy should be equal to 0. So diffusion is not 0. In this case, mass diffusion. Total mass is also not 0, which means W1 plus W2 plus W3 has to be 0. So what this means is the sum of the values inside this stencil. So W1, W2, W3 are the stencil was a 3-point stencil of this form, W1, W2, W3. So basically you are saying sum of the 3 weights inside the stencil is 0. Now this is for the case of mass conservation. So if you are looking at mass diffusion problem, you are having a mass conservation if you have a 3-point stencil with W1 plus W2 plus W3 equal to 0. Same thing applies for temperature, where if you have something like heat conservation or energy conservation, where you don't have creation of heat or sink of heat inside your heat rod. So in our example also, if we are using a 3-point stencil, then we can add the additional constraint that whatever neural networks learns, whatever the CNN parameter, CNN stencil parameter W1, W2, W3 are, the sum of those 3 should be 0. So we can enforce that. So how do we enforce that? We can enforce that in the form of a loss function. So we can introduce some loss, something like W1 predicted plus W2 predicted plus W3 predicted. We say the sum of these 3 predicted values. And then we can say take the absolute value of this, and we can say that the loss due to stencil is equal to sum of this multiplied by 100 or something like that. We can multiply this with the large number, and then we can say total loss is equal to the loss due to normal prediction. So normal prediction loss is how far away your temperature prediction is from the real temperature in the ground truth data, plus the loss due to this stencil. So we can add this additional constraint. We can actually add one more constraint, which I'm doing in the code. I will show you that in a moment. And that is the temperature, the diffusion parameter is usually not a high number. So I am saying that I'm also introducing a loss due to diffusion, loss D underscore D is equal to. So what I'm penalizing is if the neural network makes predictions where the diffusion parameter is much bigger than like something like 0.1. So usual okay values for diffusion parameters are somewhere in the range of 0.1 to 1. So I'm saying if the diffusion parameter is much greater than 0.1, I am penalizing the neural network. So what I'm doing is I'm taking a ReLU, rectified linear unit function, ReLU of predicted diffusion parameter, and I'm multiplying this by 100 or 500 or something, and I'm adding this loss due to predicted D to the total loss. So loss due to D to the total loss. So my net loss that I'm trying to minimize in my neural network training is the loss due to prediction on temperature, loss due to the prediction of weights, and loss due to the prediction of the diffusion parameter D. Now, you might be wondering, where is this prediction of temperature coming? I'll come to that in a moment. So this is the overall problem that we are solving. Now, how does the neural network look like? The structure of neural network. That's the main question here. So the structure of neural network is as follows. You have your temperature data, ground truth data, which you get by solving your neural network, right? So, solving your partial differential equation. So your ground truth data will be evolution of temperature with respect to time, given you have an initial temperature distribution, which is the initial conditions. So you have that ground truth. Then what you do is, provided a set of initial temperatures, which serve as your starting point for temperatures, you use random weights, W1, W2, W3 as the stencil. Then you apply this weight over T1, T2, T3. So this is, what is this 1, 2, 3 up to N? This is T of X at time T equal to 0, T of Xi at time T equal to 0. So this is T at X1, T at X2, up to T at Xn for initial time. Then you apply the stencil such that you get a predicted value of something that is the equivalent of dou square t by dou x square. Then you also start with a random value of the diffusion parameter. So whatever you get here from the output of this CNN, so CNN is nothing but this stencil applied over the temperature, spatial temperature distribution. Okay. Then whatever you get from the CNN, you are scaling it by the scaling factor of diffusion, which I like to denote as d cap. Then what you do is, now this you call as your predicted dou t by dou t, dou temperature by dou time. Now what you do is you numerically integrate this using maybe Euler's method. So you can say dou t by dou t predicted. So maybe I can put this as predicted by the UDE multiplied by some delta time. This is plus temperature at time t equal to 0. This is the new temperature at time t equal to t plus delta t or t1 at x equal to whatever x you are looking at, right? So you can numerically integrate, you can do this multiple number of times. So t at t equal to t plus delta t is t at t equal to 0 plus dou t by dou t predicted multiplied by delta t. If you do this once more, you get the temperature at time t equal to 0 plus 2 delta t. If you do this once more, you will get at 3 delta t. This is like called as Euler's integration. But you can do more complicated, more accurate integration called RK4, Runge-Kutta 4 method. You can use any complex meaning more accurate numerical integration technique to finally get a predicted t predicted of as a function of x comma time. Then what you do is you compare the t predicted with x comma time with the actual ground truth value of t of x comma t. How would you get this? You will get this by numerically again solving dou t by dou t equal to the known value of diffusion coefficient multiplied by dou square t by dou x square. So you can solve this numerically, this partial differential equation numerically to get a variation of t with respect to x and time. So this is the ground truth data. So these two things are compared. So this is your first loss term. Okay, so this is the first loss term, but you have additional loss term. You will have one more loss term because based on the weights, then you say if W1, W2, W3 have values, then you say absolute value of W1 plus W2 plus W3. You will say 100 multiplied by this guy is also part of the loss. Then you will say one more thing, which is a ReLU of D cap. So if a D cap is actually not D cap, ReLU of D cap minus 0.1. So I want the ReLU of this value to be not so much greater than 0.1. So here actually when I described ReLU, I don't know if I mentioned that. So here ideally, I mean what I was using was minus 0.1, something like this. So that will also be added to the loss. And maybe I can multiply this by 100 to amplify the loss. So you are really penalizing the neural network for learning a scaling factor D, which is the learned diffusion coefficient, which is much greater than 0.1. Then you are, if the D is much greater than 0.1, you will penalize the neural network a lot. So that these three terms are now the total loss. So here, what would the format of this loss be? Will it be just this minus this? No, it will be the mean squared error. So you will be doing sigma, like 1 by n, sigma I, predicted value of t minus actual value of t, the whole square. You can use something like this mean squared error. So this can be used as the nominal loss plus the loss due to weights not being 0 and the loss due to the learned diffusion parameter to be being much greater than 0.1. So these are the three loss terms which I'm using. Now let us get into the coding part of this universal differential equation, and I will also show you the results that I get. So first part of our code is importing the necessary packages. So these are commonly used packages. Most of these optimization JL, ordinary differential equation, flux.jl, etc. So just go through these packages. The best thing to do is initially don't import any packages. As and when error occurs due to package not being present, you import or use the necessary package. So that is the way in which you can learn which package is used for what. But here I will skip that. Then defining the initial condition. So the initial condition that I'm going to be using in our equation is t of x comma 0 equal to sine of pi x. So it will look something like, I have a graph here for the initial condition. I mean, I don't see it, but I can draw it. So initial condition would look something like, this is temperature, this is x from 0 to 1. So 0 to 1 is the normalized length of the rod. So here it will be, temperature will be minimum, here it will be minimum, and it will be something like this. So t of x comma 0 equal to sine of pi x, right? So sine of pi x is 0 when it is x equal to 0 or x equal to 1. So this is our initial temperature distribution. And as you know, an average temperature of this might be something like this, right? So this hotter regions will cool down to this eventually, and these colder regions should heat up to this. So eventual shape of this should be something like a flat line. That is what you should expect. And why is this? This is because of the circular or periodic boundary condition. Whatever heat is going out here should come back here. So the rod is, overall, it's not losing or gaining heat. Overall, its heat, its temperature, I mean, its energy is preserved. So here in the problem setup, we are using 0.1 as the diffusion parameter, known diffusion parameter. For what? For simulating the ground truth data. Maximum value of x is 1. Maximum value of time is 0.5. dx, the discretization in x is 0.01. This actually, when I'm running the code, I will use 0.1 because I want the code to run fast for demonstration. I'm discretizing my time domain by dividing the total time duration by 10. So I'll have 10 time points. Then my x grid is basically 0 to 1.0. Time grid is from 0 to 0.5. And the number of data points is last term minus first term divided by common difference plus 1. So first term is 0, last term is x or t. Common difference is dx or dt plus 1. So this is the number of points in our grid. Then row 0. So here row is representing t. Okay. So row 0 means t0, initial condition, initial temperature is sine of pi x. I'm also saving the data in a local folder called data. So whatever is my environment, I'll have a folder within that. So if my folder is downloads, it will be downloads/data. Okay. So that is what this data means. I'm just storing it. You can ignore these lines actually if you don't want to store the data. Then my simulated ground truth would look like this, right? So I have the domain with diffusion coefficient 0.1, time from 0 to 0.5, and x from 0 to 1, and initial condition being sine pi x, t of x comma 0. Now let's see how we can calculate numerically the Laplacian dou square t by dou x square. So the temperature we are storing in an array. So we have t equal to T0, T1, etc. up to Tn. So this is the temperature as a function of space for a given point of time stored as an n-dimensional array. Now let's say I have a Laplacian matrix which allow me to do Laplacian operation. This matrix is obviously, this should be a square matrix with dimension n by n. So let's say dou square t by dou x square is also it can also be approximated as n by 1. So this is n by 1, this is n by n, and let's say this is also n by 1. What would these individual elements be? We know that dou square t by dou x square can be approximated using a stencil -1, 1, -2, 1, right? So what would this look like for the first data point t0? This will be 1 times t0 plus 1, which is t1, minus 2 times t0 plus 1 times t0 minus 1. There is no t minus 1. So t minus 1 means, since it is a circular boundary condition, the previous element of t0 is the last element, this guy, tn. So this should be plus tn, right? So this should be and of course, this should be divided by dx the whole square. All the numbers should be divided by dx square. So I'm putting it outside. Now the second element should be 1 times t2 minus 2 times t1 plus t0. Like that, what should be the last element? Last element should be 1 times tn plus 1, but tn plus 1 does not exist. What's the next element after Tn? Since it's a circular boundary condition, what the next element after Tn will be T0. T0 minus 2Tn plus Tn minus 1. This is the approximation of Laplacian operator. So this is what we want to get. How can we get this? If we multiply by some Laplacian matrix and T. So this is matrix multiplication. This is n by n. This is n by 1. And the resultant is also an n by 1 matrix, which should be this guy. So what should the values inside this Laplacian matrix be? Let's say this Laplacian matrix was like this. Okay, all the diagonal elements are -2. So this is -2, this is -2, all in between elements are -2. And let's say there are two diagonals, right? Two more diagonals, upper diagonal and lower diagonal. So let's say this was 1, 1, 1, like that, up to 1, lower diagonal. Now upper diagonal is also 1, 1, 1, like that, up to 1. And all the other elements are zeros. All these guys are zeros. What would happen if I multiply this Laplacian matrix lap with my temperature matrix? What is temperature matrix? It is T0 up to Tn. What would the product be? The product would be, in this case, -2 times T0 plus 1 times T1. So the first element would be -2 T0 plus T1. Second element would be T0 minus 2T1 plus T2. Third element would be T1 minus 2T2 plus T3. Is this correct? Yes. And the last element would be simply Tn minus 1 minus Tn, correct? Sorry, minus 2Tn. So this would be the last element. So here, this is an n by 1 matrix, which is almost similar to, and of course, I have to have a divided by dx square for Laplacian. So this will be this divided by dx square, dx the whole square, not dx square, dx the whole square. So now compare this and this, these two guys. Every term is pretty much the same. This term is correct. It's the same as this, right? Same thing. This term is correct. It's not written here, but it's the same. And the only problem is the first term looks different. Last term also, because the first term here, this is different. Last term also looks different. What is missing in the first term? In the first term, a Tn is missing. If I want Tn here, the multiplier corresponding to Tn should be 1. So which means this guy, last guy here should be 1. Similarly, in the last item, T1 is missing. Sorry, T0 is missing. So if I want to bring T0 here in the last row, so here in the first row, the last item I made as 1. Similarly, in the last row, the first item should also be 1. So this also I will make as 1. So basically, my Laplacian matrix lap is primarily having 3 diagonals, the main diagonal, upper diagonal, and lower diagonal. Main diagonal will be all -2. Upper diagonal will be all 1. Lower diagonal will be all 1. The rest of the elements are zeros, except in the first row, last element should be 1. In the last row, first element also should be 1. Then if you multiply this Laplacian matrix with my temperature, we can get the corresponding approximation for dou square T by dou x square. Obviously, we should divide this by dx square. So that is what is done here in this code. We are designing a diagonal matrix where all the main diagonal ones are -2s, all the upper and lower diagonal ones are just 1, and you divide by dx square. The first element of the last element of the first row will be 1 as well, 1 by dx square. First element of the last row will also be 1 by dx square. So this is the Laplacian matrix. And to simulate our d dou square T by dou x square, we just say d multiplied by Laplacian matrix multiplied by the row matrix. Row matrix is nothing but the temperature matrix. So d is the initial value that we are assuming to generate the ground truth data. It's 0.1. Okay. So we can run the code. So first, what I'm going to do is I'll walk you through this entire code before running so that you can appreciate what each block of code is doing. So I have already run the code. It works perfectly, but I have converted it into different blocks. So in the current block, we are simulating the ground truth data used for training the neural network. So now we define the problem to be we use ODE problem from the Julia package. We pass the heat RHS. So this is the right-hand side of the heat equation. Rho naught is the initial condition. This is the range of values for my time variable. And so here, please don't confuse this capital T. In here, we are using this capital T in this simulation to describe time. So this is time. And rho is temperature. Okay. Although when we discussed it in theory, T was temperature, capital T was temperature, and small t was time. But here in the code, that is not the case. So what we have here is, this is the ODE problem. Then we are calling the solver using tsits5. This is Citaurus Rangekutta fifth order solver. So RK5, this is almost like an RK5 solver. We are storing that in the solution data, and then we are converting that into simply an array. Then we plot the solution as a 2D plot. I'll show you how the plot looks like. This is the 2D plot where y-axis is time and x-axis is the length of along the length of the rod. So initially, the middle part of the rod is very hot. So temperature is highest here in the middle part. The left-hand side and right-hand side parts are cooler. As time progresses, middle part is pretty much as hot as the left-hand side and right-hand side. So cooler regions will heat up, hotter regions will cool down. And this is the slices of the solution. What do I mean by that? At different time points, we are plotting the temperature as a function of time. So here, rho, y-axis is temperature, x is just x. Each plots are at different time points. So initial temperature distribution, if I remember, it's like sine of pi x. So sine of 0 is 0, sine of pi multiplied by 1 is also 0. In between, in the middle, it's 1. Then as time progresses, it becomes like this. Eventually, it will become just a straight line. If you plot this after a long period of time, we can do that. So now this is the ground truth data, ground truth, GT. And this ground truth we'll be using to train our universal partial differential equation neural network. Okay. So let's now look at the simulated ground truth plot as a GIF. So I have also converted the simulated ground truth as a GIF. I hope this can be played. Yeah. So this is what happens. So as the time progresses, cooler regions will heat up, hotter regions will cool down. So this is how the GIF will look like. Okay. So you can also run the code and generate the same GIF. Now let us define the partial differential equation plus neural network system. We are saying that the initial weights of the stencil is not exactly 1, minus 2, 1. It is, I'm starting with 1.1, minus 2.5, 1.0. Of course, you can start with different weights, but the farther the weights are from what is expected, the more it will take, more number of iterations it will take for you to converge your predictions. But here I'm not using exactly 1, minus 2, 1. I'm using 1.1, minus 2.5 and 1. Sum is not 0 here, so please note. But I will show you where I am defining the loss such that sum of these three numbers should be equal to 0. Then this defines the number of input channels. So kernel size is 3, kernel stride, number of input channels. So these are the initial weights. Then this is the part where we define the neural network, flux.convolution, where we pass the initial weights. We pass the, we use a D0 initial and padding. This is the initial padding. So this is the CNN, which we are using to train the neural network to make predictions for W1, W2, W3, and also for the scaling factor decap. Here, this is the bias, which is also set to be 0. This, this guy, 0.0 is the bias. Since there is no padding, the final output size will be 2 elements shorter than the kernel. Our kernel has 3 elements. Output will therefore will have only 1 element. And then we have 2 parameters that we are primarily learning. P1 is set of the weights W1, W2, and W3, and D. At the end of the day, we want these 4 numbers. We want the 3 weights and we want the D. Using the 3 weights, we can hopefully simulate the Laplacian. Using the D that is predicted, we can hopefully accurately estimate the diffusion, heat diffusion parameter. And then this is a restructuring function. Here we were destructuring. So we are defining the length of the parameter vector, which is 3. Then we are converting that into a format that we can use later in the loss function calculation. So D0, this will be used in the loss function. And the the restructured diffCNN also will be used later for making predictions. Then let's see the predictions, neural PDE structure and the loss. So here, NNODE has pretty much the same structure as that of the ground truth simulation function. So in the ground truth simulation function, this was what we used. We had heat RHS where we were passing the parameters. We are passing the time meaning the time points for which we are simulating, and the rho function. Rho function was where we were storing the temperature. Coming back to this neural network ODE, here d rho is rate of change of time with respect to temperature with respect to time. Rho is the temperature itself. P are the parameters, and t is the time from 0 to I think 0.5. Now this diffCNN and d0 will allow us to get the weights and the d0 parameter. D0 we already have because that was how we were structuring the restructuring the neural network. So this full restructure function is over here. If we pass a p vector there, it will return us the weights of the CNN W1, W2, W3, and it will give us the d0 predicted. So that is what these three numbers are. So diffCNN will allow us to get the weights. D0 is the predicted diffusion. And then here we are calculating the predicted value of the dou t by dou t. So this d rho is dou t by dou t at I. And what is that? That is equal to predicted scaling factor. So this is d cap multiplied by the stencil. So stencil is this whole guy. Stencil, if you remember, stencil of rho I or ti was equal to w1 ti plus 1 plus w2 ti plus w3 ti minus 1 divided by dx square. So this was the stencil. So here also we are using that. Here we are not using that Laplacian square matrix. Instead, we are directly calculating it. So here row of left is if you are at the first element, then your row of left will be the last element. Otherwise, it will be I minus 1th element. Similarly, row of right is if you are at the last element, I equal to nx, meaning you are at the last element of your x grid, then the next element on the right will be equal to the first element. Otherwise, it will be the I plus 1th element. So that is the definition of left and right. So W1 times row left, W2 times row current row, and W3 times row right. So there is a small difference from what I have mentioned here. I have written row W1 times Ti plus 1. So here the way the code is written is W3 Ti plus 1, W2 Ti, and W1 Ti minus 1. Both are fine. Both are no problem. Both are completely valid, and divided by dx square. So this is our stencil. So now we set up our problem equal to ODE problem of here we pass neural network ODE function, this function. Previously we were passing the the RHS function. Rho naught is the initial condition. This is our time span, and P initial is the initial parameters from the neural network. Then we solve using the solver. So this function predict NN is actually just used to call the solve function. So solve function is the solver predefined in Julia, where we are passing the problem, which is the the UDE plus universal partial differential equation problem. We are calling the fifth order Runge-Kutta. We are passing the parameters. dt is the t span divided by, I think, 10. It's defined in the first part. dt is, the total t span divided by 10. So it will be 0.05 in our simulation. You can make it finer also, but what I have seen is like it takes a long time to run the code. The shorter the t is, obviously. Then we have absolute tolerance, relative tolerance, max number of iterations you are saving at certain time points. So this is the function for that. Then you are defining the loss. And as I said, we are using three losses. One is the normal loss, which is the mean squared error with respect to prediction and the reality. So the reality is this ODE data. In fact, this should be called as PDE data, in my opinion, because it's a partial differential equation, but you are discretizing the time, right? So it could be ODE also. So ODE data minus prediction and taking the absolute square of that and sum of that. So this is like not the mean squared error. This is just the squared error summed up. Then you have a kernel penalty added. So kernel penalty is penalty due to the weights sum not being exactly 0. So we are multiplying that by 100. So we check if the sum of the weights are absolute value of sum of the weights are 0 or not. If it is not 0, you are multiplying it by 100 and you are having that kernel penalty term added to your mean squared loss. Then you have D0 penalty. This is for deviating for your predictions of the scaling parameter, which is the diffusion term, deviating from 0.1. You are squaring it and multiplying it by 500. So this is your combined loss term. And then you are calling this loss function using this loss neural network Adam. So Adam optimizer is what we'll be using. This function is not needed actually, because this function I am just using to call this loss function, but you can not have it also. Then this callback function is just for printing the value of weights and the predicted diffusion parameter at different epochs plus the loss. So here I'm just printing the epoch parameter, the sum of the weights. So we should check if the sum of the weights are initially starting with, I think it's around 0.5 or something. It should hopefully reduce to 0, close to 0. We are also printing the weights. We are printing the predicted value of diffusion coefficient, the loss, and the count, epoch count. So that is this callback function used for. And then the final optimizer. Optimizer, I'm using Adam. So here is the optimization problem that we are looking at. This is add type equal to optimization.autozygote. And let's see the function that we are passing into the optimizer. It is loss nn Adam. Loss nn Adam is this guy. And loss nn Adam calls the loss function. Inside the loss function, which is this, we have three loss terms. So that is what we are optimizing for. And then we just call the solver to solve this optimization problem, where we use Adam with, this is the learning rate, step size 0.01. This is the number of epochs, 200. And that's it. Basically, we are storing it in result underscore Adam. And then we can now create the final plot. So the final parameters, I'm just calling it as P star. It's in the result underscore Adam dot U. And dot T will give us the time points. And here, I mean, ignore this line. This is just for testing. But here we are plotting the predicted. So now we are predicting new set of time points using the predicted P star. So what are the parameters, by the way? They are weights W1, W2, W3, and then the D naught, right? So the predicted diffusion coefficient. So using these four things, we can actually predict the temperature. How? Because our predicted temperature or predicted dou T by dou T is equal to D naught predicted multiplied by stencil of Ti. And stencil of Ti is nothing but sigma Wi Ti, where W runs from 1 to 3, and this should be Ti minus 1 or Ti plus 1. And how do you get temperature from this? By numerical integration. And we are performing the numerical integration over here using the fifth order Runge-Kutta solver. Where is that? It's this guy, this predict NN. So predict NN, I'm calling here predict NN in the just before the plotting. So to the predict NN, I'm passing the final parameters. Then it gives me the prediction, and this prediction data is what I'm using for plotting. And when I plot, what I get is something like this. This is the X length along the rod, and this is the time. And this was my reference data, training data, which I created using the known value of diffusion coefficient and known Laplacian operator. And this is what I have. And after my neural network prediction, where I did not know the diffusion parameter, I did not know that the operator was Laplacian, I am able to get something that looks very similar. And here I'm plotting the temperature evolution as a function of time for the entire length of the rod. You can see that this blue guy is the initial condition. This is the neural network initial condition. They are matching pretty well. Towards the end, as you reach time point t equal to 0.5, the blue, dark blue and orange, there is a little bit of, you can see that there is a little bit of deviation. This is the dark blue. This is the orange. So it's not exact. The data simulation is not exact. In fact, I also have a GIF. I'll show you the loss, but I have also written a code which plots this as a GIF, evolution of temperature as a function of time. So yeah, so this GIF shows you the evolution of temperature as a function of time for ground truth as well as neural network prediction. They are matching pretty well. So, and the loss, as you can see from this plot here, I'm plotting it as logarithm of loss. I think it has changed by almost 2 orders of magnitude. It starts with around 500 or something. The loss starts around that. And then it comes down to, I think it comes down to 10 or something like that. So let's see. Let's run the code and see what we observe. Okay, so this is the code. I have already run it. It works pretty fast. And I'll share the code with you. But let's run it block by block. So first importing the packages, then the problem setup meaning the initial conditions as well as the values of the known value of the diffusion coefficient. Now generating the training data. So now this is the ground truth plots. So it should be hopefully displayed here. So whenever it shows busy here, it means code is running. So this is the ground truth data. Actually, you can make this more refined. The X grid can be more refined. Here I am using a grid where the delta X is 0.1, meaning it is X by 10. But you can make it more refined. You can do X by 100, anything that works for you. But for me, I want to run the simulation faster right now to show you guys. So I'm using X by 10. So it's only divided, my X grid is divided by 10. Time grid is also only divided by 10. So not the most finest of grids, but you can see this is how the heat distribution looks like as a function of X and as well as a function of time. These are the temperature evolution plots. And then if you run this, it will produce the GIF here, which looks like this. You can slow it down if you want by changing the frames per second. So now it will play much slower. So this is the temperature evolution. Eventually, it will just flatten out. Then, one more thing is here, actually, you can multiply by, let's say, 3 or 4. Then you will see like a proper sinusoidal distribution of temperature. So this is, and if I reduce the spacing between the grid points, you will see like a proper sinusoidal temperature distribution. You see? So this is now another temperature distribution which evens out like this. So, but let's go back. I don't want this 4 pi x. I just want sine pi x. And this is the temperature distribution. Then here we are defining the neural network plus partial differential equation. So that's the UDE. And nothing is displayed. It's just the function. Then here I am defining the loss plus the callback for printing the epochs. And here we do the actual optimization where we call. So I'm running for 200 epochs. This is very fast. It's very fast because my grid is very sparse. But you see that the loss in the starting is 44. Then my initial weights are 1.1, minus 2.5, and 1.0. So some of the weights are not exactly 0. It's 0.399. The initial D0, which we initialize, is 0.0. We want it to be close to 0.1. And after 200 epochs, we can check where it reaches. So after 200 epochs, what we have is sum of the weights become 0.001. So it's very close to 0. And D0, it's not still close to 0.1. It's close to 0.085. So it's like 85% there. Maybe if I run for 500 epochs, maybe this will become better. Let's see. So this can be 500 epochs. Then prediction will be even better. So this execution was very, very slow for me in the beginning. And I was struggling to get convergence. But I managed to get convergence by making my grid a little bit less dense. You can also try that. So here it will be now 500 plus 200, initial 200 plus now new 500. So almost 700 epochs. My sum is 0.001. In fact, D0 has not improved too much, which is okay. But let's anyway plot the graphs. So this is my reference training data. This is my neural network prediction. This is the temperature evolution prediction versus neural network data. And loss looks like this. It went from 1.5 to minus 1.5 log loss. And if I run the code for diffusion, see there is pretty good matching actually. The prediction, ground truth prediction and neural network prediction are matching. But the most important thing here, we started by saying we are now predicting the equation, right? We started by saying what? We said we can discover equation. Where did we discover equation here? We discovered equation from these weight parameters. Just look at the W1, W2, W3, which the neural network has predicted. So now what neural network says is W1 is 1.2, W2 is minus 2.36, and W3 is 1.15. It is not the best. W1 is supposed to be 1, W2 is supposed to be minus 2, and W3 is supposed to be again 1. So here, but this is still good enough. If you look at the paper which Dr. Chris had published, they have a plot which shows W1 plus W2, and I think the difference also, or the net sum. So that plot is over here. Yeah, this one. So here they are plotting W1 divided by W3 minus 1. What is that for us? W1 divided by W3 will be 1.21 divided by W3 is 1.154. 1.154 minus 1 is 0.04. For them, it is, again, it's also close to 0. So for us, it is 0. What is this? 0.04, right? Pretty close to 0. Similarly, for them, W1 plus W2 plus W3 is again close to 0 after certain number of epochs. So here you can see that they have probably run around 300 epochs or something like that. I have run to 500 epochs. So for us, the sum is 0 minus 0.001. Actually, we can add sum and the ratio minus 1. So let's say ratio minus 1 is ratio equal to so basically ratio equal to, I don't need an extra variable. I can just print ratio equal to W1 of 1 divided by W of 3 minus 1. So that is what they have in the paper, W1 by W3 minus 1. So now I can run the optimize this code. So here the ratio starts at 0.1. Here for them, the ratio also, again, for them also it starts at 0.1. For them, the sum starts at minus 0.4. For us, the sum starts at exactly at minus 0.4 as well. And then at the end of our epochs, it comes to, let's see, I ran a few more epochs. So that's why number of epochs have reached 1000 now. For us now, the sum reaches minus 0.0001. So very close to 0. The ratio reaches 0.05. For them also, I think it reaches pretty much there after 1000 epochs. So we are getting pretty much the same result. We don't have this plot. We don't have the growth plot. So in this paper, they were looking at an equation called Fisher KPP equation for modeling growth of population. We are not looking at that. We are looking at one-dimensional heat equation. But the graphs look very, very much the same because there is a lot of similarity between the equations. But I hope you understand where now the discovery of equation comes from. We had no idea that this was Laplacian. We thought, okay, let's try with a 3-point stencil. We have to constrain the sum of the weights to be 0 because of mass conservation or energy conservation criteria, not because it's a Laplacian. But now if you look at the sum of the weights and the ratio, they are coming out to be such that if this was a Laplacian, whatever the sum W1 by W3 minus 1 should have been, it would have been 0. And whatever the sum should have been, sum also should have been 0. We are also getting pretty much the same thing. So effectively, we are recovering the Laplacian format of the equation. We are also effectively recovering the scaling factor for the diffusion coefficient. It is the actual value is 0.01. We are getting 0.0837. So this is exactly how scientific machine learning framework allows you to extract information from data, but also keep the scientific structures intact. So we still use the partial differential equation structure, but we were able to get the format of the equation in the absence of, I mean, of course, I know that we made a lot of assumptions, but we did not explicitly assume the Laplacian form of equation, but we got it at the end of our process. So I hope you enjoyed this lecture. We will be covering a lot more scientific machine learning topics in the subsequent lectures. But it's a powerful technique. It's a very good research topic. If you are interested in SciML research, definitely do reach out to us. So thank you so much. We'll meet again in another lecture. See you until then. Bye.